Welcome back. This video is about linear regression and it's the diagnostics. In other words, how do we look at the assumptions that we've made with respect to our data and the residuals, and I'll talk about what that means in a minute. How do we assess those assumptions and make sure that the assumptions are met so that we can be sure that our model is valid, right? If this is the first time you're looking at linear regression, this is the wrong video to start on. So this video is part of a playlist. There'll be a link on the screen. Click on that, go to the beginning of the playlist and start at the beginning. You might have watched those and now you're here. Great, welcome back. Or you might know a little bit about linear regression and you're wanting to brush up on the diagnostics. If that's you, welcome. On this YouTube channel, we're creating R programming videos on everything. Okay, we're going to talk about diagnostics and the assumptions, and there really are four basic assumptions that we make, the four important ones that I want to deal with in this video. Okay, one is with respect to the relationship between the exposure variable and the outcome variable, and that assumption is that the relationship is linear. In other words, if you plot them, it more or less goes in a straight line. It's not a curved line. It's not an exponential curve, blah, 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 blah. Okay, that makes sense. We're talking about linear regression, and we'll talk about how to check that that assumption is met. The other three assumptions that I want to talk about are the assumptions with respect to the residuals. What are the residuals? And I think it's important that you have a good understanding of what the residuals are before we carry on, because they're even important in terms of us being able to check that first assumption. Okay, so we're going to get to all of this. And here I've plotted, and by the way, what you're seeing on the screen at the moment is a document in which I've got this entire lesson with all the R code and the explanatory notes, etc., etc. This entire document is available to you for free. At the end of the video, there'll be a card on the screen. You click on that card and you can go to a resource library and download this and many other resources for free as a PDF. So you can use this code and you can practice the code and repeat everything that I've been doing at home. The explanatory notes go into more detail than I'll go into in this video. Also, I only use example data sets that you have access to. So all of these data sets are built into R. If you do data, open close brackets, you can see that R has a lot of data sets built into it. And these are the data sets I use in the lessons. So you can literally repeat everything I'm doing at home and you've got access to the data. Right. Now, so without going into the nuts and bolts of linear regression, because I'm assuming you know a little bit about that, here's a linear model. This is, I think, is this from the MT-cars data set? And here's our model. And you can see that we've got all of our data points. And I've drawn a red line between the data point and the model itself. Right. And that the distance of that line, the magnitude of that line, that's the residual for that particular data point. In other words, it's the error. It's the extent to which the observed data differs from the model that we've created. Right. So the model is, sort of our best fit, our sort of best estimate of how this relationship works. But the actual data, there's a little bit of error. There's some difference from the actual data in the model, and we'd expect that in real life. And what that distance is, what that difference is, we call that the residual, right? And that's extremely important for this lesson, right? So we understand what these residuals are. Let's jump into the assumptions. The first is that this is a linear relationship. Now, I do want to say that most of these assumptions, we can get a sense of the extent to which the assumption is met simply by looking at certain visual plots and diagnostics, and we can get a sense. Looking at something is subjective. So sometimes you look at it and it's obvious, okay, there's not a problem there and all is well. But sometimes you'll look at something and it'll be a question mark, it's subjective. Your opinion might be different to mine, in which case there are actual statistical tests that you can do that give you a quantitative variation, answer to the question, does this meet the criteria of, is this a linear relationship, et cetera, et cetera. So just so that you know, down here I've shown, once you've created a model, and I've just assigned this model to an object that's called model, you can call it anything. If you say plot model, R will give you a series of diagnostic plots automatically that you can use. We're not going to talk about leverage today because that's more about outliers, but it'll give you all of these plots, residual versus fitted, and we're going to talk about that. That's an important one, the QQ plot, et cetera, et cetera. So you'll get all of these. So in other words, it's very easy to create these diagnostic plots. And in this lesson, we're going to talk about how to interpret them. But before we carry on, let's just continue to summarize what the assumptions are that we're making, and then we're going to talk about how to confirm them. So the first one we said is the assumption is that the relationship between the exposure variable and the outcome variable, or the predictor and the outcome variable, is linear, and that makes sense. The next three are assumptions about these residuals that we can see on the screen at the moment. And the assumptions are as follows. Firstly, that the distribution of the values of these residuals is a normal distribution, right? I'm assuming you know what that means, but just to remind us all, a normal distribution is kind of that bell curve, like a few values on the one side, most of the values in the middle, and a few values on the other side. In other words, if you look at looking at these residuals here, the red lines, if it was normally distributed, you'd expect a few of them to have very small residuals, so short little red lines, a few of them to have very large residuals, so those are the two sort of tail ends, and most of them to have sort of medium-sized residuals. And so you would get a bell curve, or a normal distribution. That's what you would that is a healthy thing, but we need to check that. So it's a linear model that the residuals are normally distributed. Then there's an idea that the residuals need to be homoscedastic. Okay, homoscedastic. What that means is that the variance of the residuals is spread evenly across all of the fitted values. In other words, you don't have there's no pattern to it. Okay, and that's important, right? So the values are normally distributed, and there's no pattern, there's no systematic pattern to the residuals. We don't have, most of the big residuals on the one side and fewer of them, most of the small residuals on the other side. Okay, so that's important, so that they're evenly the value of the variance of these residuals is evenly distributed across the fitted values, right? That's the second assumption about the residuals. And the third one is that they're independent. In other words, the value of one residual, so one error, so the extent to which the observed value differs from the model at one point, isn't dependent on what its predecessor was. In other words, what a residual nearby was, or at some other point. In other words, it's genuinely independent. And the idea of dependence is perhaps best understood, or easiest to understand, if you think about time series data. And actually, I have a nice example I'm going to show you, that if you've got a cohort of people and you measure them at different points in time, but you're measuring the same people. Let's imagine I'm one of those people, and you're measuring, how quickly I'm growing at age 5, age 10, age 15, and you're doing the same with a number of people. At that second set of measurements, one of the observations is still going to be about me, and the extent to which I'm growing is going to be strongly related to the previous growth rate that you measured from me a little while ago. In other words, with respect to this particular data point, there is a dependence as you go along the line, one measurement to the next, and they're not completely independent. So time series data is a good example where you don't have that independence. And again, these are things that we can check. Right, so let's start looking at some of these diagnostic plots. Like I said, now, I'm not going to go through this lesson bit by bit here. That would take quite a long time. You can download it and look at it yourself, but I've taken some of the plots out of it, and I'm going to specifically be talking about, and all of these examples, as I say, you can do at home. I'm going to, okay, here are our diagnostic plots that I was talking to you about. So if you say model, a plot, and in parentheses the model name, it'll give you these diagnostic plots. Here is our linear model. This is the MT cars. You can see those linear relationships. Now, this is one of the diagnostic plots, and this isn't one of them. I've recreated this just in a way that it's perhaps easier to see. It's a bit neater than the one that just comes out wholesale in the diagnostic plots that they give you. This is a little bit neater, but it's the same thing. And what you're looking, so let's think about our first assumption. The first assumption is that it's a linear model. So we look at it and we say, visually, it looks linear, but that is subjective. The next thing we can do is we can look at this plot. And this is an important plot because it actually applies to a few of these assumptions. So it's worth just understanding this plot quite carefully. This plot is a plot of the residuals versus the fitted values. Now, what are those two things? Okay. The residuals we've said is this red line, and the fitted value is for a value of the independent variable or the predictive variable. What would the model predict the dependent variable or the outcome variable would be? And that's the fitted value. And so this plot is the plot on the y-axis of the residuals against on the x-axis the fitted values. Right, now, how to interpret this plot? What we want to see is we want to see these residuals. We don't want to see a pattern. We want this to be random. We want it to be evenly distributed from left to right as much as possible in the context of randomness. So if it's, and we want there to be as many dots above as there are more or less below the line. In other words, when we look at this, we're hoping not to see a pattern. If you see a pattern, that suggests that there's something afoot. And it's not that easy to, there's not a very clear way to interpret what that means. If you see a pattern, there's a few things it could mean. And that's when we start diving into using actual statistical methods to check these assumptions, right? So we first check them visually and we say, look, we think, there's nothing dramatic to see here. There's no massive pattern. And let me show you what I mean by a pattern. Here, you can see here, there's a very clear pattern, and that suggests something is afoot. Right, there's some sort of systematic change as you go across the fitted values with respect to what the residuals are. There's other, let me just show you another one. That's another one. This is a funnel-shaped one, which usually means something. I'll talk about that in a second. But the point is what you're looking for is randomness here, looking for even distribution above and below the zero line and evenly distributed from left to right. And if that's the case, it suggests that this model is in fact linear, and there are statistical tests that we can do to confirm that if we think we need to. Let's go on to our next assumption. The next assumption is that the residuals are normally distributed. In other words, if you look at all of these lines and you'd have very few that are small, very few that are big, and most of them kind of in the middle. And of course you can produce a histogram to look at that. So this is a histogram of the residuals and say, well, is this normally distributed? Again, it's subjective, and it might depend on how many values you've got and the size of the buckets in your histogram. And you might look at this and you say, well, it's not completely convincing one way or the next. The next thing you can do is this, and this is called a QQ plot, okay, and these are quantile plot, and it is one of them, by the way, that pops out from your diagnostics. So in the diagnostic plots, you'll both get this residual versus fitted, and it also gives you this QQ plot. Now, what is a QQ plot? Just briefly, what you're looking for are these things to kind of the points to kind of go along this diagonal line, and that suggests that yes, this is normally distributed. But what does this mean? Quantiles are points in your distribution that divide the values into even sort of probabilities, right? So the median, for example, divides your data into 50% and 50% on either side of it. Your quartiles divided into into 25% buckets, etc., etc. And you can go into more and more granular divisions of your data. So you can take these quantiles of a distribution that so a standard normal distribution, and compare them to the quantiles of the distribution that you're trying to investigate and see the extent to which they map out. And if they map out quite well, you get this diagonal line of the fitted values, of the values. And so that's a nice indication that this is in fact a normally distributed, the residuals are normally distributed. Now, take note. Again, this is subjective. It's something we're just looking at. We could be wrong. We may differ in our opinion of how to interpret this. So once again, if in doubt, there are statistical tests that can be done that can help us make a definitive decision here. And we're going to look at all of those statistical tests in just a minute. But the visual test is the first way, and it tells us if we need to dig deeper, if we need to take a closer look. The next assumption about the residuals is that they're homoskedastic or homoskedasticity, right? And that is that the variance is evenly distributed across all the fitted values. So again, your visual clue here is that this is random, that these plots of the residuals versus fitted is random, and etc. Exactly what we were saying earlier. Again, the signal here, if the variance isn't evenly distributed, you're likely to see a pattern. One of the patterns that is quite common under those circumstances is the funnel going one way, or it could be it could be a funnel going in either direction, and that suggests some kind of systematic change as you move across the fitted values with respect to the residuals, and then you do not meet the criteria of homoskedasticity. Okay, and similarly, the same, the idea of independence. That okay. Now let me just illustrate independence over here. Remember, I was talking about a time series analysis, and this is in the lesson that you can download as a PDF. This exact plot is a time series where I think these are children. And they have something about their teeth measured at different ages, 8, 10, 12, and 14. And because individuals are related to themselves in previous measurements, there is not independence. Okay, these values are not independent, but they are dependent on themselves earlier. And of course, once again, where to look at this is this residual versus fitted. And any sort of pattern in this residuals versus fitted would suggest that perhaps there is not independence, right? There might be clumping, there's different patterns that you might see. But I think the lesson here is this residual versus fitted values plot tells us quite a lot. It's a great plot to look at and look for this randomness. And if it is random and evenly distributed, immediately we've got a lot of comfort that we think that there's likely to be independence. We think that there's likely to be homoskedasticity. We think that the relationship is likely to be linear. So there's a lot of ticks that come here. As soon as you see a pattern here, in my view, you need to step back and start doing the statistical tests that tell us whether or not we believe that these criteria are met. And we're going to have a look at that, how to do that right now. So let's start looking at statistical tests that we can use to confirm or refute whether or not our assumptions are being met. Okay, and we'll go through them very quickly. And what I want you to do is download this PDF. You'll get a link at the end of the video. Download the PDF and start doing this yourself. Actually doing it is the best way to learn, right? So the first assumption is that the linear relationship between these two, the x and the y, it's linear, and the statistical tests that we can do to check that is the Harvey-Collier multiplier test, and it's very easy to do. First of all, you need to get the LM test, linear model test package installed, right? So if you don't have it, you can do the install packages, LM test, and that will install it. And if it's already installed, you just call it with the library. I've already done that. To use it is super duper easy. It's HARV test, and in parentheses, the argument you put in is the model that you've already created, and out comes this output. Now, here's something that I want you to just pay attention to, because this is where you could get tripped up. Usually in statistics, we're wanting a small p-value, right? Because the null hypothesis is sort of the opposite of what we're trying to establish. And if it's a small p-value, we can exclude the null hypothesis and accept the alternative. With this and a couple of the other tests we're going to look at right now, the null hypothesis is actually the thing that we're interested in. The null hypothesis here for this particular test is that the relationship is linear. In other words, we want a large p-value above the alpha value of whatever the cutoff is, if it's 0.05, for example. Got it? So in this case, a p-value of 0.84 is a good thing, and it confirms our assumption that the relationship between the x and the y variable here is in fact linear. Okay? So just, I don't want you to get tripped up on that. And the next assumption is that the residuals follow a normal distribution. Okay, and let's say we've looked at the diagnostic curves and we're not sure. Here we can do the Shapiro-Wilk test. And what you apply to the Shapiro-Wilk test, it's, Shapiro.test, isn't the model, but it's the residuals of the model, right? So we've created an object called model. If you take the function residuals and apply, as the first argument to residuals, the object model, it'll produce a set of residuals, the residuals, and then you use that as the argument in the Shapiro-Wilk test, and it'll tell you whether or not those residuals are normally distributed. And once again, a small p-value isn't what you're looking for. You're actually looking for a larger p-value. A p-value of 0.1 suggests that the null hypothesis, which is that these things are normally distributed, is met, and you're happy with that. Okay, let's keep going. Residuals are homoscedastic. Again, we've got a test for that, the Bruscher-Pagan test. The function is BP test. Put into the first argument, the only argument is model, and once again, a large p-value suggests that we can accept the null hypothesis, that is that, in fact, there is homoscedasticity. So happy days. Okay, and then finally, that the residuals are independent. Now here we're not interested in the p-value. Okay, firstly, in order to do the Durbin-Watson test, we need to install the package car. We do the Durbin-Watson test and apply as the argument the model that we've created. In this case, it's model 2 because this is this data set up here that I'm working with at the moment. And here the DW statistic is what we're interested in. And if the value is close to 2, so not much higher or lower than 2, that suggests that there is independence of residuals. In this case, it's not close to 2. It's 0.89, and that's because in this particular data set, it is in fact the case that we don't have independence of residuals because there is this time series problem that I described earlier on. Okay, so that is pretty much firstly how to visually look at, and secondly how to use tests to determine whether your assumptions are met. Click on the link that you're going to see on the screen right now if you want to get hold of go to the resource library and get the PDF of this lesson. Otherwise, click on the link that'll take you to the next video, which is going to be about some of the special cases in linear regression that we look at. Okay, thanks for watching. Take care. See you in the next video. All the best. Bye.